by the way, please do complete this survey, even if you can just go ahead and complete it sooner. You don't have to wait till you turn in the module. It's just it's helpful for you to get some feedback just about how things are going and how I might be able to help you learn better and so on. So the first thing I want to say is, right, this is a lot, and don't let that intimidate you. So let me just talk through what this is that's even here. And a lot of it we've seen before, and a lot of it should be familiar to you even just from doing Haskell. Okay, it's just maybe in a different notation that you haven't. Okay, so this is just saying here's what our types look like, and we've already talked about this in class, right? When we talked about types for the simply typed lambda calculus, and then we ended up adding. So this is written A cross B, but it's the same as in Haskell, like, A comma B. It's just the type of pairs, right? And then A plus B in Haskell is written either AB. We talked about these when we went over the rules for the simply typed lambda calculus and said, okay, well, we've got these logical things, and or. What types do those correspond to? That's what we put. And then when we were like filling in, okay, what kind of things need to go in these rules to make programs that correspond to proofs for these things. This is what we kind of came up with. But again, most of these are probably familiar from Haskell, right? So we know about these, of course. This is just pairs, first, second. And the left-right thing, right, that's what came with the either type. So if you just go look up the Haskell's either type and think about how that works. And then these are the rules, like all these rules we had on the board at some point. So this is not new. Maybe I use slightly different letters for them or something, I don't know. The part that is new, we didn't talk about in class, but that also, I think the only question that really refers to this reduction stuff is one of the level 2 questions. So, but basically it's just showing like, okay, look, if this stuff is going to be a programming language, we have to say, like, what does it do? Like, what is it, if you run it, what happens? Otherwise, it's not really a programming language, it's just like a nice way to write some things down, I guess. That's all this is saying, right? So it's just like some formal rules that say, how does this work? So for example, here's a rule that says, look, if you have first applied to a pair, like this is just telling us what first means, right? First means, oh, you get out the first thing out of the pair. That's it, right? This rule is kind of boring. It's just, for example, it says that if you got first applied to something, if that something can do some computation, then you can just do it like inside the first. So it's just kind of saying we can just go anywhere in a term that some computation can happen, it can happen. So a lot of the rules are like that. We've already talked about this rule where you have the lambda applied to an argument. This just means saying you just substitute argument everywhere. And there's stuff about case, but this, if you stare at this and you think about what this means, this is just saying, what does it mean when you do a case analysis? It says, look, if the thing you're doing a case analysis on is actually a left T, then you're going to take, the branch that says what to do if it's a left T. So it's going to reduce to, this T1. There it is, T1. But we substitute in the T for X1. Again, this, you don't really need this unless you're going to do that level 2 problem. I'm happy to go over this in more detail if you want. So then let's see, so what okay. Maybe I'll just talk briefly about exercise 1, and then I can see if anyone has any more specific questions. But how might you approach exercise 1? I mean, one thing you could do is basically type this into Haskell. You have to figure out how to translate it into Haskell syntax. It's pretty similar, but it's going to be not quite the same, right? And see what type GHCI infers for this thing, right? Now, I don't want you to just write that down and then just be like, well, I typed it in GHCI. You should give me some evidence that you understand, what that, or how you got that, or how that was achieved. But for example, you're going to say things like, well, look, if we're applying first to P, then P had better be a pair. so this is a lambda, right? So this, first of all, this whole thing is a function. It's a function type. And it's from some input type to some output type. That input type has to be a pair type, because this P I can see here has to be a pair. Right? And you make those kinds of deductions. You're like, okay, how is this being used? What does that mean this type has to be? You can also see, right, that the first thing inside of P, because you're doing a case on it, that tells you something about what that first part of P has to be. And if there's some part of the type that actually there's no constraints on it, then you can just make up a variable for it. And just be like, well, it's A. It could be any type. Right? That's kind of the idea of how you might go about doing this. Again, like I said, if you want, you could, use these rules to make a complete proof tree for it. That's maybe it's helpful to look at the individual rules as you're thinking about what types things have, as opposed to like actually writing up the whole tree. But you could do it if you want. And this is what GHC is basically doing when you ask for the type of something. It's not literally building a whole tree in memory, but something very much like that. Is there any other questions about this? I don't know, probably many of you haven't even looked at it, that's fine. But I did get a few people asking about it. So. Either you can go over questions. Yes, Alex.
Number 5.
Yeah.
It's like in the hint you say it takes an extra argument length or something.
Yeah, gamma context, right.
So would it just output the same? I guess I'm kind of confused with the function.
Yeah, I mean, this is a common pattern, right, where you have a function that just is supposed to do something, but you're like, but it's going to be recursive, but during the recursion, I'm actually going to there's like an extra thing I need to keep track of, right? And so the way you do that is by just making a helper function that has the same type, except it has one extra argument, right? And then the original function, all it does is just call the helper function with the appropriate initial argument, and then your helper function actually does all the recursion. That's what I'm saying here. Infer type, it's actually just going to be a single line of code that just calls your helper function and starts it off with an empty context. Right? The helper function is going to need to have that context, so as it's going through, if it sees a variable, it can look it up in the context and say, what type does this have? Right? Does that make sense? That helps? Yeah, and definitely look at data document. I mean, right, as you can imagine, when we write the rules on the board, it's like the context is a list, but we don't actually want to represent the context as a list, and you have to scan through the list, one by one to see if the variable you're looking for is there. We represent it as some kind of dictionary or map, right, that has maps from variables to their types. And so there's you can look at the data.map, the standard map/dictionary type in Haskell. Okay, and then the rest of the hint is, you can actually look at the rules. Well, they're way up here, right? The rules that are way up here. These 3 rules. You don't have to worry about all these rules, because the version of the language I'm asking you to do this on only has lambda as an application, right? Not the pairs. If you look at these 3 rules and you think about basically, we're saying when you have gamma shows x has type A, or gamma shows something has type something, we're thinking of the gamma and the thing are inputs to the function, and then the type is going to be the output of the function. And so if you kind of read these rules that way, you're like, okay, well, if I'm given a gamma and I have an input that looks like this, how do I figure out what the output should be? And this is going to be some kind of recursive call, where I'm like, okay, let me call this function on T and see what I get. Okay. So if you squint, you can read those as recursive functions. And then we did something like this the other day in class. Hopefully that makes sense. You know what, I can't, here's the weird thing about this. Maybe one of y'all can figure this out. So I don't quite know how they did this. They basically like, it's like this program is running inside of like this kind of virtual machine thing inside this website. And so, like when you go to the file menu, you know, you can go to like save as, but you quickly figure out that like, it's not saving it on your computer, it's saving it like in the file system of this virtual machine. And I'm like, okay, but how do I actually download it? I haven't figured it out yet. Like I just like selected the text and like copy pasted it into a file, which sucks.
That's what I did.
That's what you did too? Yeah.
I was trying to do the same thing whenever you posted it originally on the website, and I was like,
Right.
I'd like to download this.
I know, right? If anyone figures it out, let us all know. Because I thought I read something somewhere that was like, oh, you can, like when I first started it, it said something about, you know, it's kind of provided as is, like don't rely on this, if, you know, be sure that you save often by doing X. And I was like, oh yeah, of course, and I just didn't read it, but now I'm like, no, I really want to know what it said, and it said save by doing X. I think this is all right. Okay, well, anyway, hopefully we can figure it out. I mean, of course, you can always like copy paste, I guess, in the last resort. I mean, you can also install Agda on your own computer. I could post some instructions for doing that if anyone wants to. It's one of those things where, like, if everything goes right, it's not hard. It's just like, of course, it never quite goes right. There's like some library that have, or like, so. Anyway, let's move on for now. So where were we? For whatever reason, we had decided, right, we had written down this data type, which we called even, well, this one is even I. That's the one that has n being implicit. And this, we're thinking of this as encoding proofs that a certain number is even. And we also then wrote this function called isEven that is just a function that returns true or false, is the number even. And let me say something about this really quick, and maybe later we'll see examples of this. I'm not sure, but you're like, what's the point of having, you know, this type representing proofs that something is even? Like, why not just have this function that decides whether it's even or not? Well, in this case, evenness is a particularly simple property, and yes, we can write a function that for any natural number will tell you for sure, after a finite amount of time, it will return true or false, is it even or not? But not all properties are decidable. So a property is decidable if you can do this. If you can, there's a function that will always, after a finite amount of time, say yes or no. Right? But many interesting properties are not decidable. But we could still say what it means to have a proof of that property, right? And then we could attempt to construct proofs. And if we do manage to construct a proof, then we know for sure that thing has that property. Or if we manage to construct a proof that it does not have that property, like maybe we can do that. But there's not necessarily any function we could write that would tell us yes or no, because it might not be possible to do that, right? And so, yeah, for evenness, it doesn't actually make that big of a difference. But for other things, it's actually important that we can say what we'll accept as evidence for that thing, and then we can attempt to construct evidence, but we don't know up front whether we're going to be able to or not. And there's no way we could write a function that would tell us. But we can attempt. But anyway, so what we're trying to do is to basically prove that, like, isEven will return true if and only if there's a proof of it. So we want to know that this function and the proofs kind of mean the same thing. You know, because maybe imagine that this was a much more complicated thing, and we weren't sure whether one or the other we had done it correctly, and so this gives us additional confidence that we've done it correctly. If we kind of define it in two different ways, and then can prove that they're the same, and we're like, okay, well, it's still not a proof that it's the right thing to say, but at least I got them both wrong in exactly the same way or something, which is less likely. So we wrote down this type of equality. Don't worry about how it works too much, right? But the point is, we can now reason about when things are equal. And we proved that it is transitive. We could also prove that it's reflexive. It would be very similar. So now we can actually write down this thing we prove. So I'll say isEven. I'm going to name this is the theorem, right? But I'm naming it basically like isEven if and only if I. Actually, no, yeah. I'm actually going to make two different, so we're going to make two different ones. It'll be easier for now. We can talk later about like how would we write down an if and only if version. So isEven implies even I says, isEven n if isEven n is true, then even I n. This is for all n. Okay, write that. Right, it says, look, if you give me an n as input, then I will give you back, right, if you give me an n and you show me that isEven n is true, then I'll give you back a proof that n is even. And then the other way is going to say, yeah, for any n, you give me an n, you give me a proof that n is even, and I will give you back a proof that isEven returns true on n. Although names are declared but not accompanied by a definition. Yeah, I know. All right, well, I was just, making sure that, I was like, wait, is it capital T true? Yeah, apparently it is. It would have yelled at me otherwise. Okay, so how do I start? Pattern match, it's always the answer. Okay. Here's a slightly more interesting question. What do you think we should pattern match on? Only two choices. Okay. Oh, we can just try it and see. All right. Let's say n. You would say n. Okay. Yeah. I think n is going to be a better choice. The way to think about that is, well, if I pattern match on EQ, it has to be ruffled. That's the only thing it could be, because that's what equality is like. But like there's not really, if I had isEven n somewhere, and then, it could like replace it by true. But I don't really have isEven n anywhere. My goal is just mentions n, it doesn't mention isEven. So that wouldn't really help. And we could try it, right? If I say EQ pattern match, actually it's not even, it's like, I don't know, I'm not sure that'll work, right? It actually gives us an error. So, that didn't work. What was that?
The error message is pretty funny.
Yeah, I'm not sure if there should be a fix for this, because I get stuck when trying to solve it. It's very, very human of it. It's like, poor Agda is confused. There's an error message that GHC famously gives. It's like, you try to do something, and it's like, what does it say? It's like existentially bound variables inside of pattern content, or something, I don't remember what it is, like makes my brain explode. It's like, don't do that. it's not actually GHC whose brain is exploding, it's like the person who was writing the code who's just like, I can't understand this. Just like, no, I'm not gonna let it. Even though like in theory it could work, but I don't know how to do it. So no. So let's talk about an n. Okay. Because of course, right, n we're going to like both of these things is even n. Oh, okay, and here's a different way. Here's a more positive way. So like the negative way to know that we should pattern match on n is that pattern matching on EQ doesn't seem like it'll help and it doesn't work anyway. The more positive way to know that we should pattern match on n is to say, okay, both is even n and even I, both of them are kind of defined by matching on n, right? So is even n, it pattern matches on n to see what to do. And even n kind of pattern matches on n to see what kind of, constructors you can use. So we're not going to be able to make any progress unless we also pattern match on n. And then, so let me make this bigger. Okay, so now in this case, right, when n is 0, it says my goal is to prove that 0 is even, and I'm given a proof that true equals true. Right, why did it turn into true equals true? Well, because when n is 0 specifically, it kind of reduced this, according to the definition of is even 0 is defined to be true. And so it's like, hey, you're given that true equals true, we're like, great, that doesn't help, but I need to prove that 0 is even, and that's easy because there's one of the constructors, ZE, says that's exactly what it is. So I can just say like Control C, Control A for auto, and just spell right. Okay. Now in this case, I'm given that is even of successor of n is true. And I have to prove that successor of n is even. And actually, let me. I wanted to be able to see the definition of is even over there. So. Any ideas how I should proceed from here? So the thing to notice here is that, this says is even successor of n, but like this hasn't reduced at all. Because is even doesn't know what to do yet. Because if you look at the definition of is even, well, we've seen is it 0 or successor, but just if all we know about this is that it's successor of something, is even doesn't yet know how to reduce, right? Because the definition says it actually does more another pattern match, a nested pattern match, and it says, no, I need to know whether that n is 0 or itself a successor. So again, we're not really going to be able to make much progress with this proof unless we do another pattern match on n to see which of those cases we're in for is even. So I can tell it to pattern match on n again. Notice, do you see what happened there? See how it only gave me a case for some n, it didn't give me a case for 0? Anyone know why? That's kind of neat. So if n is 0, that means is even of suck 0 is false. Right? And we have a proof here that is even n is true. So in that case, this reduces to false. So that means we would be given a proof that false equals true, and it's like, that's not possible. So So that can't actually happen. So you don't have to deal with that case because it's obvious that that case is impossible. That's pretty cool. So now, all we have left is we're given a proof that isEven n is true. And notice, right, this is a little tricky to think about, I guess. This n here is not the same as like this n up here, because this n here, we pattern matched on it. So maybe I should let's call this something different actually. I think this will help. And you're welcome to do this. We'll call this like n prime. If I reload Control C, Control L. Right, it says, okay, my original n, we now know is equal to successor of n prime. Or maybe I should call it like n minus 2. How about that? Let's call it n minus 2. Okay, so now it says, right, this, we had a proof that isEven of successor of n minus 2 is true. But isEven of successor of n is equal to isEven of n. So it reduced that, and it's like, yeah, now we know that isEven of n minus 2 is true. And we have to prove that successor of n minus 2 is even. The way we prove successor of something is even is with that SSE constructor. So if I refine this, right now I just need to prove that n minus 2 is even. Maybe is how I'm going to prove that n minus 2 is even. Right, exactly. This function that we're writing returns proofs that something is even. Right? So originally I was trying to make a proof that n is even, and now it's telling me that, you know, I now need to prove that n minus 2 is even. Right? But what is this function needs a proof that that thing is like isEven of that thing is equal to true, but I have that here. It's exactly what I have, right? So if I make a recursive call to this with this thing, with this proof, it'll give me exactly this. Right? And ultimately you can see that, like, how does this work? It pattern matches on n, and if it's 0 it stops, it's done, and if it's a successor of a successor, it recurses, and then like it keeps taking off, you know, 2 successors at a time until it gets all the way down to the bottom. So if I say isEven I, close this down. I want n minus 2 here, and I want 2. And I don't know, I wonder would it do that automatically? If I said auto, would it? It actually fills it, like auto works. In fact, auto probably would have worked for the whole thing. Auto, you know. I'm not sure when Agda's auto search is or isn't willing to fill in a recursive call. Obviously, in certain cases it is, right? So it did that here. I think there's like ways to give it hints when you're like, do an auto search, but hint, you might want to use this function. And then it'll like try to use that function. Because in general, it won't try to use every possible function. You can imagine it would blow up if it tried to use every possible function it could to try to search for a proof. I mean, it would just get, there'd be way too many possibilities. All right, so all right, move the other direction, a little more quickly, but yeah, and I definitely encourage you to, you can go play with this yourself later, like try deleting the definition and see if you can reconstruct it yourself, right? Go back in. You know, maybe try, and if you get stuck, then you can go back and rewatch this part of the lecture, and then like, delete it, try again, to make sure that because like, this is definitely one of those things where you can watch someone do it and be like, yeah, that makes sense. Then you get around to actually doing it yourself, and it's a different thing. So you can try. So, again, we need to know what n is for this to make any progress. In this case, when n is 0, again, my goal is just to prove that true equals true. So that I can do with REFL. Again, I need to pattern match, have a nested pattern match on n again. Again, it didn't, I'll rename this -2. It didn't give me a case for suck 0. And this time, it's because it could tell that if n was suck 0, there couldn't possibly be a proof that n is even. And so that case is also not possible. And then, so now my goal is to prove that isEven of n minus 2 is true, which I could do with a recursive call, but in order to do that, I would need a proof that n minus 2 is even. Okay, but this is not a proof that n minus 2 is even. This is a proof that successor of n minus 2 is even. So, any ideas where I could get a proof that n minus 2 is even? Think about what could E possibly look like? What are the different ways that we could construct even I something? Do you remember how that works? Here's even I. So it could be Z is a proof that 0 is even, but that's definitely not this, right? This isn't 0, so E can't look like that. Otherwise, it would have to look like SSE, but that means what would it have inside of it? It has to have in it a proof that, 2 less than that is E. So this thing, E, has to look like SSE applied to some proof, and that proof inside of it is exactly the proof that I want, to pass to the recursive call of this. So I just need a pattern match on E. It says, okay, in fact, E has to look like SSE or something. And now that, which it is now called E, I'll call it E prime. E prime is exactly what I want. Say even I, even of n minus 2 E prime. I'm going to put a space in there. There we go. And I think, actually let's, pretty sure if I just try auto right here, I don't think it's going to work. There's no solution found. Because, it tries, but it can't figure out how to, where to get, this argument, the recursive call from. We have to actually pattern match on E first to kind of bring that thing into scope so that it can then use it. So if I pattern match on E, I think now if I do auto, it should work. It should find it. Yeah. Okay. So, right, a lot of this is pattern match on stuff. Think about the types of things that you have and the types of things that you want. Take advantage of the fact that Agda is keeping track of all the details for you in terms of what is it you have to prove? What do you have that you could use, right? Yeah, that's kind of some of the tips on how to do this. All right, let's do one more proof about this before next time we move on to some other stuff. But the way that I wrote isEven This is one way you can implement isEven, and I implemented it this way on purpose so that it would correspond nicely to our proofs of evenness, right? Because the proof of evenness like goes by steps of 2, and so I also wrote this in such a way that it kind of goes by steps of 2, right? Where every time it makes a recursive call, you know, it says, it does 0 and 1 in special cases, and then it does a recursive call on n minus 2. So I knew that that would make the proof work out nicely. However, there's another way we could write isEven, and I want to write that, and I want to prove that other way of writing isEven gives the same answer as this version of isEven, and so we can kind of connect all three of them that way. And then doing that proof will show us a few other things that will be useful later. So, so we'll call this isEven 2. So this way, I'm just going to say, look, if n is 0, then it's true. But if n is odd, I'm just going to ask if n is even, and then just do the not of that. So I want to say, not is even to n. Does that make sense? So intuitively, it seems like this should give us the same answer as that other isEven. But we want to see if we can actually prove that. So we want to say isEven equals isEven 2, which says for all natural numbers n, isEven n equals isEven 2n. Right. So we're gonna need some other things, but we're just gonna start and see kind of what issues we run into, what we might need. So, and this is, I'm not just doing it this way because I'm presenting it in class. This is the way that I would, anytime I wanted to do a proof in Agda, I just write down the thing I want to prove, and I just like try to start, and then just kind of see where I get, and that might give me some hints like, oh, maybe this is a lemma that you might want, or like you need to prove some more facts about this thing first so you can use it, and then I would like leave some holes there and then like come back, because it's nice that you can just leave some holes. You don't have to like comment out the code. It's just like, yeah, this code is still there, it's checking it, but there's just a hole here, it's not finished, and I can come back and fill it in later. So of course we're going to start by pattern matching on n, because both of these functions pattern match on n. So okay, so in this case my goal is true equals true, because both of them are defined as true on 0, so there's nothing really to do there. So great, I already done one case. Alright, well if n is so notice this one, like the isEven 2 has already reduced. It's not isEven 2n. But isEven doesn't know what to do yet because it has to pattern match twice to like decide what to do. So we might as well go ahead and pattern match twice. So in this case, okay, my goal is false equals false. That makes sense, right? Because they both reduced, like isEven reduced to false. That was one of the base cases. isEven 2 was like not of isEven 2 of 0, which is not of true, which is false. So that's easy. What about this one? So now my goal is that isEven n equals not isEven 2n. So why would this be true? Why is it true? Well, like what facts do I need to know in order to be able to convince Agda that this is true?
Right. You need to know the double and not with that.
Yeah, so we need to know that like not of something is equal to that something, right? So that can be a lemma that we can prove. And then we'll be left kind of needing to show that isEven n equals isEven 2n, but that's just a recursive call to this. That's just like, yeah. So let's prove our little lemma. So we'll call it not. And I want to say for any Boolean, and I think I'm going to say b that order, not the other, because I just happen to know that that's going to be a little easier for us. Of course, either order would work. If we do it in the other order, we might end up needing symmetry of equality, and so we would have to define that also, but just so you don't have to flip it. Okay, well, how do we prove this? I need to prove that B equals not B. Well, this is actually very easy. I just pattern match on B. And in both cases, it can just evaluate not of that and see what it is. So true equals true. False equals false. Done. So that's really just kind of a proof by cases. It's like, well, there's only two possibilities for B. In either case, this works. So yeah, I'm thinking.
Something I'm noticing, I guess I didn't pick up on it earlier, when you're like defining a function like not B, like the last part, B equals not B, so you don't have to, well, it makes sense, you don't have to give it that other B, like that B equals not B is like one argument.
Yeah, well, this is the output of the function.
Okay.
Right, this function takes an argument B of type bool, and then outputs a proof. It outputs a value of this type, which we think of as a proof that B equals not B.
Okay, so that's a type of it.
Yeah, remember, I mean, everything is types. All these things are types, but we're playing around with this Curry-Howard isomorphism that says we can think of types as propositions, and we can think of values of those types are proofs of those propositions. So we can think of it either way. You know, from one perspective, we're just writing programs with certain types. From another perspective, we're proving stuff because that's kind of how we set this up so that they correspond. Okay, so how do I actually use this lemma? Well, we're going to use the fact that equality is transitive. So if I call this thing recursively, that will tell me that isEven n equals isEven 2 of n. And then this tells me that isEven 2 of n equals not isEven 2 of n. And then like I can chain those two things together to conclude, you know, that first thing is equal to that last thing. So there are nicer ways to do this kind of proof. I don't think we might talk about them actually, because it's kind of fun, where you can actually write proofs kind of in the style where you say, you know, this equals this for this reason, equals this for this. You can give a chain of things, and you don't have to literally say trans of whatever. But for now, we're just going to do it explicitly. So I want to say trans, and trans, right, takes two equalities and returns like the bigger equality. So the first thing I want to say is that this is my recursive call on n. Says okay, and then if you look here, right, what am I left with? Right, I'm left with the second part, which says I have to show that isEven 2 of n is not isEven 2 of n. And that I can just do with this not thing. So if I say not. Actually, wait, let's try something. Just because I'm kind of curious. And if I say auto, so Control C, Control A, I think it's not going to succeed, but I'm not sure about that. Maybe it's clever. No, it didn't find it. Again, this is because kind of by default, it's only willing to do like kind of some basic pattern matching, maybe a recursive call, putting together arguments you have, but it's not going to try using like all the other functions you have defined because it would just blow up the space of possible things for the search. But I think what I can do, if I type in not, I'm like, hey, hint, you want to think about using this not thing, because I wrote that as a lemma for this case. So try using that and now do an auto search. So if I hit Control C, Control A now, see now it finds it. It's like, oh, now I'm going to do an auto search, but I'm willing to, you gave me a hint that I might want to use that function, so I'm going to try things with that function and see what it does. Yeah. So cool. So yeah, but the point is now we've proved that. So first we proved that this this isEven function, which we implemented in this slightly funny way, to make it match the even I proofs, that they were about the same thing. But then we also proved that this more natural, maybe more natural implementation of isEven actually behaves the same as that other one. And so kind of they're all about the same thing. I suspect if we had tried to directly just prove like this about isEven 2 here, we probably could have done it, but I think it would have been a little more awkward, rather than kind of breaking it up into steps. Cool, any other questions about any of this? I think next time, I think one of the things we're going to do next is we'll actually like write some functional programs, things like map, and like see if we can maybe prove some theorems about like how map behaves, or things like that we might actually care about in a program if we want to prove that our program is correct. Kind of see if we can do that. This was just kind of to get us